So this is going to be an exercise problem on multiple linear regression, and we're going to have two explanatory variables, and they are both going to have a numerical or a ratio type level of measurement. So researchers want to investigate this linear association, they claim that there is, between these explanatory variables and a response variable, and that variable must also be, of course, for linear regression, must be continuous numerical. And so they give us the solutions there, or the summary of the results, and we see that we have to use a 5% level of significance, and we are free to assume that the assumptions for the use of the parametric tests that we want to use are met. So we see a sample size there of 100 subjects, and then we see a results table of the model, and that shows an intercept estimate of negative 66.6198 and its standard error of 113.275. We see the two coefficient estimates and their standard errors as well. Of course, there's got to be a coefficient estimate for each one of our explanatory variables. Then we see also the sum of squares total. Remember, that's the squared differences between the actual response variable values and the mean for that variable. The SSR, the sum of squares due to the regression, that's the sum of the squared differences between our estimate for the response variable and the mean for the response variable. And we see the SSE, that be the sum of squares due to the residual or the error, that is the sum of the squared differences between the estimate for the response variable and the actual values for the response variable. And so we see all those values there. We note that there are 4 questions here. Let's look at question number 1. Test the claim of the researchers that at least one of the explanatory variables is linearly associated with the response variable at the 5% level of significance. And we see a nice hint there that we can use the F-test for that. Question number 2 would be determine and interpret the coefficient of determination, that's R squared, for the model in question 1. And then we see a little note: if you reject the null hypothesis in question 1, then you can proceed to the rest of the questions. Remember, in a setting like this, we are going to reject the null hypothesis, and we will go ahead and do these. So determine if each explanatory variable is linearly associated with the response variable at the 5% level of significance. So do remember, we'll have to reject the null hypothesis for our F-test before we look at the individual coefficient estimates. And then also determine the 95% confidence intervals for these coefficient estimates. Your course might require you to do these confidence intervals or not. If you don't have to, then you can certainly skip that part of the video. And then question number 4, write a mathematical equation that shows the estimate response variable value given the coefficient estimates using the results of the model. So we just want a nice little equation there: y hat sub I equals beta sub 0 hat plus, etc., etc. We'll have a look at that. And in part 2 of question number 4, we want to interpret the results of the coefficient estimates. We need to understand what these mean, especially now that we have more than one explanatory variable for our linear regression model, and then calculate the estimated response variable values, or value it should say, I think, given a value for the explanatory variable of 105 and a value of, that's the first one, and the second explanatory variable value of 49. So we can use our model to calculate an estimated value for our response variable. So we'll keep those questions in mind. Let's try and do them. So here we go. I've got the exercise problem here. I've got a little bit, copied those results down. We have 100 subjects in our study. We see the SST, SSR, SSE there. And of course, remember, the sum of squares due to the residual and the sum of squares due to the error. If you add those two, you should get the total sum of squares. And if you add these quickly, you'll see the 372,000 and the 904,000. They add up to 1.277, etc. million. So that's fine. And then we get, I've just rewritten the little model here for us. Remember, when you use software, you'll get this kind of model. So you'll have the intercept and then your two explanatory variables there. I've named them x sub 1 and x sub 2. So this problem doesn't put any specifics to the problem, not a little public health or other data scenario. We're just trying to keep it very generic here so that you can use this approach to solve any similar problem. We see the coefficient estimates there. And let's look for another pen. Do remember, if you see a table like this, that means this will be beta sub 0 hat. Beta sub 0 hat, this will be beta sub 1 hat, and this is going to be beta sub 2 hat. And here we're going to see the standard errors, the standard error of beta sub 0 hat, the standard error of beta sub 1 hat, and the standard error of beta sub 2 hat. And these two slopes, remember, that'd be the slope for the first explanatory variable, the slope for the second explanatory variable. And in a table like this, it's very easy to calculate the t-statistic, because any statistic here is just going to be the coefficient estimate divided by its standard error. So let's have a look at question number 1. I think we've got enough information here for our usual step number 0, because in step number 0, we just want to write a summary of everything. I think we've got most of it. Perhaps the one thing we can add is that our alpha value is 0.05. So we've got the summary, nice, all the values that we would need to do this problem. So let's start with step number 1. Step number 1 is what are the population parameters that we're interested in? And the population parameters are going to be these slopes, aren't they? So that's going to be beta sub 1 and beta sub 2. And those are going to be, remember how we interpret these slopes, they show us how the response variable changes for every 1 unit increase of this explanatory variable associated with this slope after adjusting for the other variable. And the same for beta sub 2. So you can write that out. But in principle, we're thinking about these two population slopes. Let's do step number 2. Step number 2. We're going to write in step number 2 our null and alternative hypothesis. So in our null hypothesis, we're going to say that all these slopes, let's just write it out, all these slopes are 0. And in any model, if you multiply by 0, that's 0, which means irrespective of what the actual value of these values are, they don't change, or they have no effect on the response variable. And so let's do our alternative hypothesis, at least one slope is not 0. We're not saying one of them, which one it is, or both of them. If you had more, we just say at least one of them is not 0. Let's look at our step number 3. Let's have that was our alpha value. Our level of significance is 0.05. Step number 4. In step number 4, we have to say what test we're going to use. We're going to use the F test. And there are multiple assumptions. And in follow-up courses, we talk about investigating our model. So we'll definitely investigate assumptions as far as our residuals are concerned, etc. That's not part of our course here. We were just told that these assumptions are met. But if you're interested, any quick search on the internet will tell you the assumptions for the use of these tests. And of course, you can look those up. So we're going to use an F test. Step number 5 is what is the test statistic and how is it distributed, and we calculate that statistic. So let's write that down. I like to do all my definitions and formula in green. So remember the F statistic, that is going to be the sum of squares due to the regression. Let's get a ruler out and try and keep things neat. And we're going to divide that by the numerator, nu sub 1, the numerator degree of freedom. That gives us, the numerator, by the way, that gives us the mean squared error due to the regression. And we divide that by the SSE, sum of squares due to the residual or error. And we divide that by nu sub 2, and that is described by the F distribution on these two parameters, nu sub 1 and nu sub 2. Those are the two parameters under the null hypothesis. If the null hypothesis was true, that is what our population looks like. I would to repeatedly sample from that population, calculate this F statistic over and over again. Given that the null hypothesis is true, that all slopes are 0, I'm going to get a distribution of F values, at least a theoretical distribution that will describe all these possible F values that I can get. So let's do the following also. Let's just say nu sub 1. How do we calculate the numerator degrees of freedom? That's going to be k minus 1. And for the denominator degrees of freedom, that's going to be n minus k. And one thing we could add here right at the top, let's add something else. We had our alpha value. We could also have k in there. That's the number of parameters in our model, and we can count them. There's 1, 2, 3 parameters in our model, 3. So that means we can do all of these calculations. Let's do nu sub 1 first. That is going to be 3 minus 1. That's going to equal 2. And nu sub 2, that's going to be, well, we had 100 minus the 3 parameters in our model. That's 97 degrees of freedom. So we can say here that our F statistic was going to be described by the F distribution on 2 and 97 degrees of freedom under the null hypothesis. So let's calculate our F value. So we're going to have to get a calculator out, and let's have a look at it. So here we go. Let's see. We've got our values here. Let's go to our calculation section. I'm going to say, okay, let's put that inside of parentheses. So we're going to start with the SSR. That's 372.863.395. We're going to divide that by our numerator degrees of freedom, which we said was 2. Okay, let's go outside of those parentheses because we're going to divide that by, let's put the denominator in its own set of parentheses there. We need the SSE, there it is, 904.595. Oops, that's wrong. So let's just go back, 904.595.971. And we want to divide that by the denominator degrees of freedom, remember, which was 97. 97, let's have a look at that, 19.991. So let's do that. It's about 19.991. And let's go to step number 6, where we want to use our decision rules. So you should recognize the fact that that's quite a large statistic, and we are going to reject this null hypothesis. So let's have a look at it. So step number 6, that is our decision rules. Now you can do a critical value approach or a p-value approach. We're just going to do the critical value approach. Let's have a look at our calculator and see if we can get the critical F statistic. I'm going to go to the home button. Let's go down to distributions. Click OK. I'm going to go down, down, down. There we go, F, Fisher's F. I'm going to click on that. Our numerator degree of freedom was 2. Our denominator degree of freedom was 97. Let's click, go down to next. Click OK. Now, we want that upper tail. We want to go towards positive infinity, the upper tail. So let me just go back to this little section here. Click OK. So this is what I want, the upper tail. So let's go down to the upper tail. And we want some value of our statistic. Unfortunately, this always says x, but that's the f that we want. But we want that to be equal to, so I've got to go right to the end, 0.05 is our alpha value. If I click on OK, we see our test statistic needs to be larger than 3.090. So imagine that just said f. So the probability that f is larger than 3.09. So right about there, that's going to be 0.05. So all this area under the curve here, that makes up 0.05 or 5% of this total area under the curve. And this curve is the curve of the probability density function, very specifically for the two parameters 2 and 97. So let's write our critical F value, F crit, and that is going to be 3.090, and now by our decision rule, our F statistic is larger than the critical value. That means we reject the null hypothesis, and we accept the alternative hypothesis. At least one of these slopes, we don't know which one, at least one of the slopes is not equal to 0. So we can interpret that as we have a useful model here. These two explanatory variables, if we look at them in combination, somehow they are linearly associated with the response variable. So if we write step number 7, which is our conclusion, we're going to say, I'm just going to write it out, and I'll forward the recording. So we have for step number 7, there's enough evidence in the data at the 5% level of significance to show that at least one of the explanatory variables is linearly associated with the response variable. And by that, what we mean by that is in the population, at least one of these slopes, at least one of them, is not equal to 0. Good. In section number 2, we've got to calculate the R-squared value. So let's write that down, the coefficient of determination. We need to interpret the coefficient of determination. So we'll have, so let's just write down the equation for the coefficient of determination in green, all my formulas and definitions in green. That's going to be the SSR divided by the SST. So we interpret that by saying it is the proportion in the total variability of the response variable that our model, our regression of y on x, well, both of these variables x, explain. So let's calculate that. Let's do R squared. Oh, that's the wrong color. That is the wrong color. R squared. Squared, that equals. Now we just have to look at what the two values were. Let's take our calculator. Let's go back. Let's take our calculator. Let's go back home, and we're going to click on the calculations. And we're going to say 372. It's our SSR. 863.395. We're going to divide that by the total variability. Remember this total variability, the difference between what the actual value is and what the mean for that response variable is. I'm going to square those differences, add all of them. So that's 1,277,459.367. And if I get that, that's a very low score. That is 29. Let's write that down. It is 0.292. That's about 29.2%. So we're going to interpret that as saying our model explains only 29.2% of the total variability in the response variable. Now we have more than one explanatory variable, and you can just add more of these, and you need to penalize that. This number can artificially, I'm going to just say artificially, grow just because we add more of these. So what we want to actually calculate is the adjusted R squared. So let's say the adjusted coefficient of determination, and there's various algebraic forms of this formula. I'm going to use this one, 1 minus, and that's going to be 1 minus R squared, n minus 1, divided by n minus k. So there we go. And so let's calculate those values. Let's bring in our calculator again. Let's do this. Let's say it's 1 minus, and let's put that in parentheses. Let's do another set of parentheses. We're going to say 1 minus, and then our R squared, which we just had, that was 0.292. And let's go outside of that set of parentheses because we want to multiply that by something else, which is n minus 1. Remember, we had 100 subjects minus 1. Let's go outside of that parentheses because we have to divide that by something else, and that's n minus k. That's 100 people in our study minus our number of parameters, which is 3. And if we execute that, this is what we're going to get. We get an adjusted R squared value. Let's just put that out in percentage. That's 27.7%. So see how that has gone down? We are penalizing the fact that our model has more than one explanatory variable. So now we can say, according to the adjusted R squared value, that our model only explains 27.7% of the total variability in the response variable. So now let's carry on with the problem set. We have rejected this null hypothesis in our F-test, this analysis of variance, and we see that we rejected that null hypothesis. So we know this model is a good model, and now only can we start interpreting these individual slopes. Don't jump to these slopes first. For each of them we can calculate a t-statistic, and we can compare that to a critical value, and we can express if we have enough evidence in the data at the 5% level of significance to show that this one and or this one is linearly associated. We do our f-test first, and now we can interpret these individual values. Now this is a large amount of work, especially if you have more than two. Two is already going to be a lot of work. We'll have to go through all the steps for both of them. So let's start with the first one. Let's get the pattern going, and so I'm sure that if we just do one, that you'll be able to do the other one. So that is going to be a t-test, because we're going to be able to calculate a t-statistic. So let's start with that. Let's start then with step number 1 for this test. What are the population parameters? Well, the population parameters in this instance, we're just going to look at beta sub 1, the slope. And we're going to say that is this change in the average value for the response variable for every single unit increase in the explanatory variable associated with this coefficient after adjusting for the other variable or variables if you have more. So let's do step number 2, the null hypothesis. The null hypothesis is going to be that beta sub 1 equals 0 in the population. Alternative hypothesis for two-tailed beta sub 1 is not equal to 0. Step number 3 is going to be our alpha value. We were told to use a 5% level of significance. Step number 4, we were told that we can just assume that these assumptions for the use of this test is met, and we're going to we'll just call it for now, we're going to call it a t-test. Step number 5, now of course that is a special type of t-test. We'll just call it a t-test. So let's put it in green, our formula. We're going to say that t equals, well, we're going to take that beta sub 1 hat, that estimate, and we are going to divide it by the standard error. We don't have to worry about how that is calculated. We get that from our table. Standard error of this estimate. And that's going to follow a t-distribution on a certain degree of freedom. Remember, t-distribution only has one parameter under the null hypothesis. Imagine this null hypothesis was true, that this was really in the population. If we were to repeatedly sample 100 subjects from this population, create your model, calculate an estimate for this value, that distribution of all of those, this is what it would look like. And remember here, our degrees of freedom for this f-test, this t-test is going to be n minus k. So let's have a look at that. So let's calculate our t-statistic here, and remember this is still for beta sub 1. Let's have a look at that. We said that was very easy. We just take that coefficient and we divide it by its standard error, and it's right there. There we go. Let's do 4.5047. We're going to divide that by its standard error, which is 1.0096. And that gives us a t-statistic of 4.1101. Good. We have our t-statistic. Let's do step number 6. That's going to be our decision rule. So we need to calculate a critical value. And remember, this critical value, we have to do that for two-tailed alternative hypothesis, so alpha divided by 2. And our degrees of freedom is 97. It's n minus k. So let's have a look at that. Let's go to the home button. Let's scroll down to distributions. There we go. Okay. I'm going to go down to the t distribution, students t distribution. I'm going to hit OK. Our degrees of freedom is 97. I'm going to click on OK. And let's go to this little section there. I want to look at, let's look at the upper tail. I'm going to go down so that I can get the upper tail. I'm going to say OK. And then I want to scroll all the way to the top. And I want that top alpha divided by 2. So I want that top value so that I get 0.025. I have to divide my 5% on both sides. Remember, if I click OK, we can see there it is. So this area under the curve, that'll be 2.5% of the area under the curve. It's a 95% confidence interval. So we have to think about splitting our 5% on both sides. This is a probability density function for the t-distribution on 97 degrees of freedom. Remember, the total area under the curve is 1. I'm just looking for these intervals of least probable t-values under the null hypothesis. And we see our critical value there, 1.985. So that is going to equal 1.985. And by our decision rule, we see here that our t-statistic, remember we want the absolute value of our t-statistic, if that's larger than the critical value. Now we're going to, we always want the positive one there. We're going to reject the null hypothesis, and we're going to accept the alternative hypothesis. The alternative hypothesis is that this slope in the population, beta sub 1, is not equal to 0. We're going to accept the alternative hypothesis. So we can have step number 7. I'm going to write it down. I'll forward in the recording again. So keeping it very generic, I'm just going to say there's enough evidence in the data at the 5% level of significance to show that the population slope for the variable x sub 1 is not 0. Now, you can expand on that, and please do in the exam, especially if you get a question which doesn't state generic variables such as this. If there's a little story behind it, such that this might be age and x sub 2 might be blood pressure, etc., you'll have to write those out. And remember here, we are saying that this is adjusted for, and let's explore that though in the next question. But before we get there, let's have a look at just calculating the confidence interval for this specific coefficient. And I'm going to write it there. We want the 100. Let's do that. It's going to be the 1 minus alpha times 100%. So alpha was 0.05, 1 minus 0.05 is 0.95 times 100%, so that's the 95% confidence intervals. So how do we calculate that? We're going to say beta sub 1 hat plus or minus some confidence coefficient, and that'll be some specific t-value for alpha over 2, given our degrees of freedom there, times the standard error of that test statistic. Now we do remember, I'll just do it in red just to be sure, just so that you can see, this is our confidence coefficient C that we always talk about. And because we use the same alpha value here, that is reflected, this confidence coefficient, as this critical value. We're saying we want to be 1.985 standard errors away from 0. We want to be 1.985 standard errors above and below this value for the 95% confidence intervals. So in our case, that is going to be beta sub 1 hat. Let's go all the way back and just see what beta sub 1 hat was. There we have beta sub 1 hat 4. So it's going to be 4.5047 plus or minus, plus and minus, so lower the upper and the lower bounds. This it's going to be the same value as that, 1.985 times the standard error. And let's just make sure that we copy down the standard error correctly again. There's our standard error, 1.096. 1.096. So there we have, let's do the lower bound and upper bound. Just as an exercise, I'm going to go back home, going to go up to calculations, hit OK. Let's do the lower bound. That's going to be 4.5047. There's going to be minus, let's put that in parentheses, 1.985 times 1.096. We close that, and we're going to see that that gives us the lower tail here. That's going to, on the lower side, that's going to be 2.3352. Let's do the upper. That's going to be 4.5047 plus 1.985985 times 1.096. Close that. 6.680. So that's our 95% confidence interval. We are 95%. Now remember, we usually use these words, but you know what that really means. If we were to do this over and over again, in 95% of cases, these different intervals that we will find will contain the actual beta sub 1. But we usually just use the words we are 95% confident that the beta sub 1, the population slope, is between 2.335 and 6.68. And notice that 0 is not in this interval. 0 is a bit lower. And that supports the fact, or that's just a different way of noticing the fact that we can reject the null hypothesis. So you would have to do exactly the same thing for all the other coefficients that you have, coefficient estimates that you have. I'm just going to do this one. I'm going to leave it to you to do the other one, and you will have to see whether you reject the null hypothesis, accept the alternative, or if you fail to reject the null hypothesis. I'll just leave you with the other t-statistic. That's going to be negative 5.156 if you just do that quickly. And of course, we want the absolute value of that, and you're going to see that that's also larger than the critical value. So you're going to reject the null hypothesis for the second slope as well. So in part number 4, question number 4, let's write out our mathematical equation. I'm going to write it out first in green. Let's do red because this is not a formula. This is just going to be, this is just the model that we get mathematically from this. We're going to say, as far as our response variable is concerned, we're going to get for a certain individual, we're going to get an estimate for that. That is going to be, take our intercept beta sub 0 hat, the estimate of that. We add to that beta sub 1 hat, the slope for this first variable, for this ith individual, plus beta sub 2 hat for our second explanatory variable, again for this ith person. That is going to be our mathematical model from the results that we do have. So in our case, let's write that out. We're going to say, well, we can always create an estimated value for, remember that's going to be as close as possible because we use ordinary least squares, so these are the best possible values, such that this is as close as possible to what the actual value for this individual would be, y sub I. And that is going to be, now we have to look at the results we were given. The intercept was negative 66.6198 plus 4.5047 times whatever the value is for that person, whatever their value is for that first variable, and then minus 3.5766, and then whatever their second variable value is. So that is our model based on the results that we have. So how do we interpret these two slopes? So we're going to say 4.5047, that's our beta sub 1. We're going to say, I'm saying beta sub 1 hat, this estimate of what the slope would be in the population. In our instance, from our data, it's 4.5047. That is the change in the estimated response variable value for every 1 unit increase in our first explanatory variable after adjusting for the other explanatory variable. And the same for the second slope estimate. Negative 3.5766 is the change in the estimated response variable value for every 1 unit increase in the second explanatory variable after adjusting for x sub 1. Remember, if you were to build a model and it only had this one explanatory variable in it, this value, beta sub 1 hat, would not be 4.5047. It'll be different, but we are adjusting for this presence of the other explanatory variable. And we have to add these words to interpreting what these results are. So it's saying whatever this x sub 1 variable is, after we adjust for or keep the other value fixed, remember, is what we really do. We say for every 1 unit increase in this, after adjusting for x sub 2, the response variable value will go up by 4.5047. So this value that we calculate here from this equation will go up by 4.5047 for every 1 unit increase of this variable after adjusting for x sub 2. And the same here, that for every 1 unit increase in x sub 2, we're going to see a decrease in this estimated value of negative 3.5766. And what this reflects is two slopes. And because we have these two explanatory variables, we are going to think of our model as this flat sheet in three-dimensional space, and we're looking at two slopes in two perpendicular directions. And then finally, we ask can we calculate an estimated value? So let's take this person, let's calculate an estimated value for this individual, for that response variable. And we're just going to use the model that we've had. It's negative 66, negative 66.6198, 6198. We're going to add to that 4.5047, 5047. And now for x sub 1, we're going to plug in 105 in our model. Then we had beta sub 2, which was negative 3.5766, 3.5766. And for x sub 2, we have the value 49. So let's see what for this individual, we're using our model now as a predictive model. If we have these two values, what is the predicted response variable going to be? So that's a negative 66. So let's do that, negative 66.6198. And I'm going to add to that the following 4.04. Let's do that, 5047. I'm going to multiply that by 105. And we're going to subtract from that. Let's do 3.5766 times 49. We close our parenthesis and we look at that. That's 231. This person will have a response variable, an estimated response variable or predicted response variable value of 231.1203. And that's it. That is our problem with the multiple linear regression when we have two explanatory variables and both of them have a ratio type level of measurement.